We were introduced to combinations, and again, the key thing about a combination is that the order doesn't matter. We already saw the formula for combinations. This line shouldn't be there and there. So if you have n items and you choose all of them, 52 cards, choose all 52. The order doesn't matter. How many ways can you do that? Only one way. Take them all. 52, choose one. How many ways could you choose one card? That will always be n. And what we have at the bottom is the mathematical or formulaic proof for why n choose n minus r is always equal to n choose r. With numbers, it's even easier to see. If you have 10 choose 6, it will equal 10 choose 4. 10 choose 2 will equal 10 choose 8. Because the bottom numbers always add up to the number on the top. So we will look at poker hands. How many poker hands are there? So you pick 5 random cards. I've pulled out 5 random cards right here from a 52 card deck. There's 52 cards in poker. The order does not matter. So you have 52 cards. You choose 5 of them. Oh, I think this is where, let's see how close I am on this one. This is where the numbers from the last one might have confused me. Is this the right number on this one? Yes? Awesome. So just about 2.6 million different poker hands. So what you're about to witness right now as I show you these 5 cards, the chances of me getting this are 1 in 2.6 million. I have the 9 of diamonds, the king of spades, the 3 of clubs. I know the excitement is going. The queen of clubs, and the queen of diamonds. All right. 1 out of 2.6 million hands. You will probably, even if you play poker for a very, very long time, not see this hand maybe ever again. Soak it in, enjoy it. But it's not really that exciting of a hand. Maybe that's what makes poker so interesting, is that there's so many possibilities. A committee. So when you see the word committee, that could be one of the triggers for yourself to think this is a combination. Because a committee doesn't matter, or a group of people doesn't matter the order. 2 boys and 3 girls is to be chosen from a class of 15 boys and 18 girls. How many ways can this be done? Well, we have to decide on our boys. 15 choose 2. And our girls, 18 choose 3. 2 different decisions, so we'll multiply them together. When do we multiply and when do we add is a thing that you really have to think about. Here, we don't have different cases. Cases is where you add things up. And cases is when you've completely counted something. So have I, after doing 15 choose 2, have I completely considered a whole committee? No, I only have part of the committee. So I have 2 decisions that I'm making here, so this will be multiply in between them. A group of students must be separated into 3 smaller groups. Group A, 8 students. Group B, 5 students. Group C, 7 students. How many ways can this be done? Well, if we think about decisions, how many decisions do we have to make here? We have to make a decision who's going to be in Group A, who's going to be in Group B, who's going to be in Group C. If you're choosing Group A, how many choices do you have right off the beginning? Order doesn't matter. 20, choose 8 of them. And then if you choose group B next, how many choices? Why 12? 8 are already in group A. So we're left with 12, and we need to choose 5. And group C, okay? Now, if you're in this class, 20 people, group A, I choose 8 people. I say you're in group A. And then there's 12 people left. And of those 12, I say, okay, you 5 are in group B. And someone is still sitting at their desk going, I wonder what group I'm going to be in. I wonder what group I'm going to be in. Right? What's going to happen to all those people that are left? They're all going to be in group C. Now, if I do 7 choose 7, that's only one way, right? Well, whoever's left is going to be in group C. That should make sense, that there would be only one choice left at the end. Now, if we multiply these all out, we get a nice big number. If I'm asked to simplify this with my formulas, this one's going to be 20 factorial over 8 factorial 12 factorial. This one's going to be 12 factorial over 5 factorial and 7 factorial. The bottom numbers always add up. And the last one's going to be 7 factorial over 7 factorial and 0 factorial. Bottom ones have to add up. What cancels out? The 7s. Anything else? The 12s. And that's it. What is 0 factorial equal to? 1. So this simplifies to 20 factorial over 8 factorial, 7 factorial, 5 factorial. Does that remind you of anything? Have we ever had questions that look like that, the answer? What kind of permutation question look like this? Repetition, identical objects, right? So could we solve this same question as an identical objects? Well, if you took those 20 students and say, line up from shortest to tallest, they'd be in an order. And then you cut pieces of paper and put down 8 A's, 5 B's, 7 C's, put them in a hat, and pulled letters out of the hat and gave the first person the first letter all the way through. Does it make sense that how many different words using the number of different words that were possible or arrangements of that would be 20 factorial over 8 factorial, 7 factorial, 5 factorial? So we could solve this question as a combinations question, or we could think of it as an identical objects. And permutations and combinations sometimes do that. You get more than one way of trying to figure something out. Find the number of poker hands with no clubs. So if I took this deck of cards and I wanted to get no clubs when choosing 5, how could I do that? What would I have to do to this deck of cards to make sure that when I pick 5, I don't get any clubs? Take out the clubs. If I took out all 13 clubs and then choose 5 cards, would I be guaranteed not to get any clubs? Yes. And so the number of poker hands that have no clubs, take the clubs out, 39 choose 5, and this is a beautiful number. Isn't it? Isn't it pretty? the number of hands with no clubs. Okay, and for this last question, I am going to be a salesperson, and I'm going to try to sell you correct solutions. They may or may not be correct. You have to listen to my logic and agree or disagree. I'm going to give you 3 pitches. There's a possibility that all 3 are correct. There's a possibility that all 3 are wrong. There's a possibility 1's correct and 2 are wrong, or 2 are correct and 1 is wrong. You have to decide. So we want to find the number of poker hands with at least 1 club. So I'm going to do, this is sales pitch number 1. Sales pitch number 1. I want to get at least, so I'm going to take out all the clubs here. I want to get at least 1 club. So I take out the 13 clubs. Perfect. There we go. And if I want to count all the hands with at least 1 club, what I'm going to do is, of these 13 cards, choose 1 at random. So that'll be the start. 13, choose 1. Then I, for sure, have 1 club, right? Because I chose it from the 13. I take the other 12 cards, I put them back in the deck, shuffle things up a little bit, and then choose 3 more cards. When I choose 3 more cards, I could get another club, but I wouldn't have to, right? It could be that I don't get, or I have to choose 4 more cards because it's a poker hand of 5 cards. So I choose 4 more cards, and I could possibly get another club, which I did. I got the jack of clubs. But now my hand has 2 clubs, and that's fine. So it has at least 1 club. So what did I do? First, I did 13 choose 1 to get 1 club, and then I put the other clubs back in. I now have 51 cards left because 1 of the clubs is taken out, and I choose 4 more of them. And putting this together, 2 decisions, gives me the total amount of hands with at least 1 club. That's sales pitch number 1. Sales pitch number 2. Well, just before I counted how many hands had no clubs. So I'm going to use the not strategy. I'm going to count all the poker hands, 52 choose 5, and I'm going to take out the bad ones, 39 choose 5, because we counted that before as the number of hands without any clubs. If I take all of the poker hands and take out the ones without any clubs, what's left have to be ones that have at least 1 club. Strategy, sales pitch number 3. Sales pitch number 3, I'm going to use cases. I'm going to count 1 club, 2 clubs, 3 clubs, 4 clubs, 5 clubs all separately and add them up, and that will give me the total amount that would have at least 1 club. So in case 1, so it's really similar to number 1, just a little bit longer. Case 1, I'm going to choose from my 13 clubs 1 club, and from my other 39 cards, choose 4 more. That would be all the hands with 1 club. Case 2, and I'll do this quick. I'm going to choose 2 clubs, and from the other 39 cards, choose 3 more. Case 3, choose 3 clubs, and from the other 39 cards, choose 2 more. Case 4, choose 4 clubs, and from the other 39 cards, choose 1. And case 5, is where I get all 5 clubs, so I don't have to choose any from the other 39. I add up my cases, and that would give me the total number of hands that have at least 1 club. So there's my sales pitch. If I'm a good salesperson, I hope you believe that all 3 are correct. And I would never try whatsoever to confuse you or trick you or anything like that. What do you think? All right, so now we have the results. And since the results are not all the same, we have the possibility. What possibilities? We do not have the possibility now that all 3 are right. We still could have all 3 are wrong. We could still have 1 right and 2 wrong, or 2 right and 1 wrong. Can anybody give me a logical reason why they know something is right or something is wrong? Well, what's your logical reason? 2/3 probability. You better. No, that's not a logical reason. How many poker hands were there when we figured that out earlier? No, that was the poker hands without clubs. But total poker hands. 2.6 million, right? What does that tell you about one of our, or a couple of our answers? This is way too high. You can automatically say this one is wrong because it's more poker hands with at least 1 club than there are poker hands in total. The logic of that should be bad for you. You cannot have more poker hands with 1 club than there are total poker hands. So this one's wrong. It is true that these 2 are correct. So now the question is, what went wrong in our logic? Because I thought I was a pretty good salesperson, and you guys had your gut feeling, oh, I like number 1. What went wrong? Well, sometimes when you do combinations where the order doesn't matter and you make separate decisions, sometimes you can accidentally create order. And I'll show you how it happens. So in the 13 choose 1, I choose a club. Which club should I pick? 3 of clubs. I picked the 3 of clubs. That was my first one. Then I mix the other clubs back in, and in my 4 other clubs I get the ace of diamonds, the king of hearts, the 7 of spades, and the jack of clubs. That's one possibility. Now in my 13 choose 1, is it possible I could have chose the jack first? So I could have chose, this is a bad J. Okay, there we go. I could have chose the jack first, put the other cards back in, and chosen the ace of diamonds, the king of hearts, the 7 of spades, and what's going to be the problem? The 3 of clubs. In this method, those would have been counted as different hands. But in reality, are those not the same? So the reason we got 3.2 million is because we counted a whole bunch of hands more than once. And the reason that happened is that there was overlap in our decisions. We could have chosen a club in one space and then chosen that same club later. Causes a problem. Whereas in the cases, there's no overlap. These are clubs, these are not clubs. These are clubs, these are not clubs. And so in that way, we maintain the order not mattering, whereas in the other one, we didn't.